Fastball for you. And this guy, French guy, I don't really know how to say his name. I'm under the impression the French can make any letter silent at any time. So maybe his name is utterly silent. I don't know. But we're going to start as we did last time by looking at the data. So here I have the data that I'm going to graph. You can see the pressures need to go from 1 to 2.4. The temperatures need to go from 250 to 4.25. So I'm going to, on my graph here, graph an annotation tool. Pressure versus temperature. So my pressure is, well, that's it. How do I grab an annotation? There we go. Favorite color? I heard purple. So pressure is here, temperature is here. Our pressure is in ATM. I'm not sure how well I can write that sideways. You can always use the paper. There we go. Temperature's got to be in Kelvin. Just like with Boyle's law and the ideal gas law, we got to be working in Kelvin. Kelvin is the only temperature that gases actually are directly proportional to. Anyway, moving on. So for my pressures, I'm going to start with 1, 1.2, 1.4, 1.6, 1.8, 2.0, 2.2, 2.4, 2.6. I did count ahead of time. I know this would be 0.8. So I'm not starting at 0, 0, and that's okay. I'm just made sure my data fit the distance of my axis. Okay, here also, again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I've got 10 and I've got to go from 250 to 425. So that's a difference of 225. So if we divide by 10, I need to go by 22.5. Well, that just doesn't sound fun. So what we're going to do is we're going to go by 25. And I don't have to start at 0. So I'm going to start at 250 and then go to 275. And then I have 300 and 325. And then I have 250 and 375. And then I have 400. And then I have 425. And then I have 450. This would be 475. Way over here, I'd have 225. It's all good. Our data fits, and that's what matters. And now we're going to graph, and you can see it's a very obvious relationship, and that's why we do the graphing, so we can see the relationship between pressure and temperature. So I would get a straight edge, don't do like I'm doing, get a straight edge and draw that from edge to edge of your graph. That should have been a perfectly straight line. But here's the key, all right? It shows that temperature goes up, pressures also go up. So pressure and temperature are directly proportional. Okay. And that's why we graph. Like we can find out the relationship, we can figure out a formula just based on how the data graphs, which gives graphs a lot of power. All right, so I'm going to move on here and actually show you the, here we go. Oh, I forgot to clear my annotation. Still group of two. Where my annotations go? Let's try this again. Annotate. Here we go. I want to clear. Oh, my drawing. Here we go. Okay, sorry about that. Okay, so we're going to move on now. So I have a demo. Okay. And it may not be easy to see with the camera here, but I have a strip thermometer. And right now in my classroom, you can see, I don't know what kind of hey, focus is right about there. So it's the color here is on 20 degrees Celsius. Okay. And I have a 2-liter bottle, it's been open to the atmosphere, and I'm putting the lid on it. Okay. So I have my 2-liter bottle. I know you're gonna just be awed by my artistic ability here. I know you don't have to tell me. Let's do a new color. Let's go hot this time. So I have my 2-liter bottle and draw a 2-liter bottle from like that. Okay, I know it's awesome. Isn't it? Yeah, okay. And I have a thermometer in it. So here's my thermometer. And inside are some gas particles. Okay. And inside are 5 gas particles, if I just spell like it. The pressure is normal atmospheric pressure. And that in normal cases, that's actually low pressure. Okay. The temperature is 20 degrees Celsius. Now, yes, we should turn that into Kelvin. Okay. So that's 298. Oh, no, 293. I totally messed that up. I'm going to try 293 Kelvin. There we go. Now, this is a special lid. I don't know if you've ever seen them. These are called fizz keepers. You can buy them on Amazon. And they're always there. So when I was your age, and please don't ask how long ago that was, this guy came up with this idea of, I'm tired of my 2-liter bottles of soda going flat. And they go flat because you release the pressure that comes inside, which is true. So he came up with the idea that what if we had a way to repressurize it? Would that keep it from going flat? Well, that's a great idea, absolutely. Turns out it doesn't work so well. But what it literally is doing, I am pumping air into my bottle. And I don't know if you can tell already, but the temperature in my bottle is changing according to the thermometer. So now I have a lot of air in this bottle. Okay, so I'm going to make a new drawing. Here's my after. I have a lot of gas particles. So first off, I need my 2-liter bottle, and I know you're going to be odd. Here we go. And I have my thermometer strip. And now I have lots of gas particles and lots of pressure from those gas particles. Okay, they're all over the place. And the temperature, okay, so pressure in the bottle is now high. If I try to squeeze this, it doesn't work well at all. Pressure is very high. So what's the temperature? So here's the fun part. I get to look at my thermometer, and my thermometer says 26 degrees Celsius, which of course, let's convert to Kelvin, 299 Kelvin. Okay, so check out, just by putting some pressure in the bottle, I've changed the temperature of the gas in the bottle. Now, what's going to happen when I release the pressure? You're going to hear a psh, right? And then, okay, don't know if you heard it. It did make the noise. And then the thermometer, if I held it here long enough, you would see it start dropping back to room temperature because I've released the pressure. So as pressure goes up, as I pump gas in, the temperature also goes up. So as I released it and the pressure goes down, the temperature is also going down. It's a direct relationship. Both up, both down. So let's talk about that mathematical relationship. I remember to clear my drawings this time. Here's our mathematical relationship, and this is the way it always looks when we have two variables that are directly proportional. We have them on opposite sides of the equation, if you will. In this case, we write them just for order. Well, I didn't mean to do that, so sorry. We write them for order on this side and this side. That's what we do, okay? So P1, T1, P2, T2. We have a pressure before and a temperature before, pressure after, temperature after. Again, pressures are usually going to be measured in atmospheres or millimeters of mercury, which is the exact same thing as before. We've got two names for the same thing there. Temperature must be in Kelvin. So we're going to do some examples here. And this is a picture I took from the top of Mount Monadnock. I spent 2 summers in New Hampshire, and I one day climbed the mountain. They have like one mountain, and it's really ironic. It's like a gravel road all the way to the top, and then you have to like someone cut in some stairs with a rock. And because I live in Colorado, those are mountains. But this is literally like the highest point in all of New Hampshire. I'm told in that picture there somewhere, it's 4 states that you can see. I mean, obviously New England states are like this big, not like Texas, but it is what it is. One of those summers while I was there, a park ranger, sorry, a record was set for the highest temperature change recorded on top of that mountain. So let's go over that, okay? So what if a park ranger parked his Jeep up at the top? Because you could pretty much almost get your vehicle up to the top. It was a weak climb, but so temperature is going from 1 degree Celsius to 30. And the Jeep tires, usually, you know, you start off, you want your cold tire pressure. That would have been like 42.1 PSI is typical for that kind of vehicle. And we want to know what's going to happen to the Jeep tires, okay? So my equation is P1 over T1 equals P2 over T2. So I'm going to plug in my pressure 1, which is the original cold pressure. And I know I'm not using atmospheres or millimeters of mercury, but I wanted to put it into terms that you're probably used to. And we started at 1 degree Celsius. Oh, let me put the 0 for sig gauge. And then we want to know what that new temperature, that P2 is, when we hit 30 degrees Celsius. Okay. So we're going to do a multiply divide. We're going to multiply across and then divide for x. So it's 42.1 PSI times 30 degrees. That decimal should be down there, sorry. 30 degrees Celsius equals 1 degree Celsius times our x. So I'm going to multiply these two and then divide by 1, which isn't, you know, going to change. Okay. So here I go. 42.1 times 30, and my answer is 1,263. So my pressure to 1,263 PSI. Because Celsius. So those car tires, which are holding at the morning 42 PSIs, now have to try to hold 1,263 PSI. So guess what's going to happen in those car tires, right? Nothing, because I did this problem wrong. That's what I want to show you. Don't do it this way. Did you catch what I did wrong? I hope you were yelling at the screen that I was doing it wrong. Okay, I do not use kelvins. And that is the only proportional temperature that's valid for gases. So P1 equals P2 T2. Okay, so 42, again, 42.1 PSI. 1 degree Celsius, 274 kelvins. And then I'm looking for pressure 2. And 30 is 303 kelvins. Okay, so now I'm going to cross multiply divide. So 42.1 PSI times 303 kelvins, 303 kelvins equals x times 274 kelvins. And I'm going to solve for x. I'm going to take 42.1 times 303 divided by 274, and I get 46.6. So those car tires, which cold tire pressure was 42.1, now have to hold 46.6. No big deal at all, right? I mean, car tires are going to inflate that with that much more pressure just from the heat of driving and the friction. So this was done wrong, just to show you, you've got to use kelvins or it's going to go bad on you. You're going to get very, very wrong answers. All right, thank you. Let's move on. I'm going to clear away my annotations and let's do our next one. Okay. So P1 equals P2. And when you're on paper, this is what I like to do. I like to see, okay, I'm going to circle a number or box a number with its label. And I have a number with its label, and I have a number with its label. Now I'm going to decide what they are. 4 is a pressure, so that's a P1 and a P2. And this is the temperature and T1. And so I'm assuming I'm looking, yes, I'm looking for T2. And it doesn't really matter what you call the 1s or the 2s, as long as you keep the pairs together. This is coming to me at it with the pair, because that's the word at, so this and the question. Okay, so let's plug in our numbers for pressure. 8084 divided by 223 Celsius. I'm going to add 273 to that. Okay, I'll come back and add that in just a moment. And then I get 4044. And my X is now my temperature to my new temperature. Before I move on, I'm going to add my, wow. Okay, I'm going to have my 223. It helps if I can type it in correctly. This is 496. So, okay. I'm again going to cross multiply and divide. So 496 Kelvin times 4044 equals X times 8084. So I'm going to divide both sides by 8084. Because that extends to cancel the 1 here. And that's all for my answer. So X, which is temperature 2. And check out the labels, okay? 4, cancel 4, so that gives me kelvins. That's really good. I want kelvins because I'm looking for a temperature. We've got 496, 404, divided by 808. And coming in temperature Kelvin, okay, 248 kelvins is what I get there. Okay. So that's it. That's all I have to do. Here's my answer. It is that easy. I started with 3 sig gigs on everything, so I'm ending with 3 sig gigs and I'm all good. Okay, let's move on to the next one. I hope you find that these really aren't scary at all. The biggest issue is actually figuring out what am I given. That really is truly the biggest issue. If you can figure out what you're given, you're good to go. Okay, so now the communication. So again, I'm going to circle numbers with their labels. Okay, my circle has to kind of like be broken. There we go. I have 2 temperatures, so I'm just going to call this one T1 and this T2. Now I want to read carefully. This is a pressure, but this is a pressure at the warmer temperature. So these two go together. So if this was T2, this is P2, and I'm then looking for P1. That's what my question mark is. Okay. So P1 over T1 equals P2 over T2. And I'm looking for P1. That's supposed to be 1 there. So there's my X. My temperature 1 is 93, and I need that in kelvins. So 273 plus 93, 366 Kelvin equals 820 millimeters of mercury, also known as a torr, divided by, I need my new temperature in Kelvin. So I'm going to have 273. Don't you love how easy that is? I wish like Kelvin had been the original temperature scale, and then we wouldn't even have to do any math. It's great, but no, it came after all the others. Okay, I'm going to multiply across those two, and then I'm going to divide. So 366 kelvins times 820 millimeters of mercury equals X times 406 kelvins. Now check this out. I'm going to divide by 406 kelvins, which is good news because my kelvins are going to cancel and my pressure unit is all that's left. And I was asked for pressure. So I wanted that. And I also want 3 sig gigs. All right. Actually, I take that back. This is 2 sig gigs. We're going to run into 2 sig gigs. That's what we're so 366 times 820 divided by 406, and then rounding to 2 significant digits. Now check this out. 740. Because sig dig, placeholder 0 doesn't count. I need a label, millimeters of mercury. That is my X, which is my pressure 1. So originally it was that 740 millimeters of mercury. That easy. There we go. It really, gas laws are fun because they're really simple and straightforward. You just plug in what you're given and you crank out your answer. Now the catch is And I know this is a battle. You've got to be careful with figuring out what am I truly given to work with and what goes with what. Okay, last one we're going to do together, and then you'll be practicing on your own. So let's see, for my final color, I pretty much used all the good ones. I might as well just go for white. Here we go. All right. So I have one atmosphere at 25 degrees Celsius. So that's a pressure, and I'm just going to call it P1, and that's the temperature I'm going to call T1. Doesn't really matter as long as I keep the pair together, and this is obviously a pair. And then here's my T2 because it's my other temperature. And so I'm looking for the new pressure, so that's P2. Okay. So P1 over T1 equals P2 over T2. And I have one atmosphere. Over is 25 degrees Celsius, that's 298 kelvins. Now, by the way, that was 4 sig digs, that was 2 sig digs, and that was 4 sig digs. So at the end, I'm going to go with 2 because I multiply, divide, I go with the lowest. But anyway, moving on. Looking for the new pressure, that's my X. And I'm at 75 degrees Celsius. So I'm going to go 75 plus 2, 73, and I have 348 kelvins. I'm going to cross multiply. 1 atmosphere times 348 kelvins equals 298 kelvins times X. I'm going to solve for X by dividing by 298 kelvins. Okay, and even the kelvins, I just scribbled them out there ones. So X, which is pressure 2, is going to be 348 times 1 divided by 298. I can actually 6 times 1 in my calculator. I'm down on 1 point. If I'm 126, 1.2. Okay, well, that didn't cancel as atmosphere, so that's what's there. Now, I want to, you get to check your work with gas laws. Okay, we know the relationship, direct relationship. So the temperature went up, my pressure should go up. I don't even know. I'm gonna I put the button on my pen and suddenly it's not doing what I wanted to do. Okay, it must have clicked off the end of it. Anyway, my temperature went up, my pressure should go up. So I started with 1 atmosphere and now I'm at 1.2. So yes, it did go up. Now that doesn't guarantee I have the right number exactly, but it absolutely does tell me that I'm doing the math correct because I got the correct proportionality. All right, so you will have practice to do probably in Canvas, but that's GayLussac's law. I'm not French. I don't know how to pronounce it correctly. You're welcome to correct me if you do know, and I wish you good luck.